about that again. So I'll go through this quicker than anticipated because we had a bit of a delay. But basically, I'm just going to review for your test. This is all of section 3, and that's the only thing that will be on your test. So mostly it's going to be electrophilic aromatic substitution reactions. One of the big ones we learned is nitration, which your electrophile in nitration is the nitronium ion, NO2 with a positive charge, and the catalyst to use is sulfuric acid. So here's a general equation. You have a benzene or a substituted benzene aromatic ring with nitric acid here in sulfuric acid, and that will give you nitrobenzene. So here's the mechanism for this. This is nitric acid, and when you protonate nitric acid from sulfuric acid, you'll protonate this oxygen here, which will give it a positive charge, okay, which then will make it a good leaving group. So this nitrogen-oxygen bond can then break and give you water and nitronium, which is your electrophile. Okay, so now that we have our electrophile, now we can go through with the actual substitution with benzene. So here's your benzene ring. Air will go from the double bond to the electrophile, and the electrophile center here is nitrogen. Okay, so that's what's actually going to be connected to the ring. Okay, so that breaks this double bond here. Okay, so we add our nitro group to one of the previously doubly bonded carbons, and then a positive charge forms on the other one. This is your benzenium intermediate. Okay, that's true. That exists with all EAS reactions. They always have an intermediate benzenium cation. Okay, so then this carbon hydrogen bond breaks. Okay, which will, those bonding electrons will go in between here to reform that double bond, which will also neutralize that positive charge. This gives you nitrobenzene, and then your hydrogen ion back, which we use as a catalyst up here. Okay, everyone following me? Okay. So the next one is halogenation. Okay, so general, we have benzene with either chlorine, bromine. This is our catalyst, is aluminum bromide. You can also use aluminum chloride, and then you end up with a halo benzene ring. This is bromobenzene. So your mechanism here, and your electrophile here is a halogen cation, and then catalyst is the aluminum chloride or bromide. So you have your halogen molecule. These both have 3 lone pairs of electrons. Okay, one of those lone pairs of electrons will go to the aluminum to form a bromine aluminum bond here. Okay, so you have a negative charge here, positive charge here, which will cause this bromine to bromine bond to break. Okay, so these bonding electrons will go to this bromine, and that will break off. Okay, so we end up with a bromine cation and then this anion. Okay, and this right here is your electrophile. So again, now that we have our electrophile, now we can go through with the actual substitution. So the air will go from the double bond to the cation, okay, which will break this double bond and add the bromine to one of the doubly bonded carbons, and then a positive charge will form on the other one. And here, you don't always have to show this step. It's kind of up to you if you want to or not. But what actually happens is this anion from here, this aluminum bromine bond will break and take that hydrogen, which will form HBr, and then reform our catalyst. But basically the same thing happens where the hydrogen comes off and the bonding electrons go to reform the double bond, neutralize the positive charge, which will give you your substituted benzene. Okay. Okay, if I'm going too fast, let me know, but we've done these kind of mechanisms a lot, so these shouldn't be too much of an issue for you. So sulfonation, our general reaction is we want to add this sulfonic acid group to the ring, and we do that by reacting benzene with sulfuric acid fuming, which means that it has, so we have sulfuric acid, but it has this SO3 in it. That's what fuming means. It just has this compound in the sulfuric acid. So this is our electrophile, and we know we have that because it's fuming sulfuric acid. Okay, so this is the structure of that. This is the structure of that electrophile. You have a sulfur double bonded to 3 oxygens. Okay, and this sulfur is, or these oxygens are more electronegative, so this sulfur is electrophilic. So air will go from the double bond to the electrophilic center, which is the sulfur. Okay, and that will break one of these sulfur oxygen double bonds. Okay, so we break this double bond and this double bond. Okay, I left out a positive charge there, but so we add the SO3 to one of the doubly bonded carbons. Okay, which this actually has a negative charge because we broke that sulfur oxygen double bond. So this is the actual structure of that now, and this oxygen is holding a negative charge. Okay, but again, we have a positive charge on the other previously double bonded carbon. This hydrogen, this carbon-hydrogen bond will break. Those bonding electrons will reform this double bond, and that hydrogen will protonate this oxygen, which will give us our sulfonic acid group. Okay, any questions so far? Okay, so these ones are just a tiny bit trickier ones, but Friedel-Crafts alkylation. Our goal here is to put an alkyl group on a benzene ring, and we do that by reacting a benzene ring with an alkyl chloride. Okay, so our electrophile is a carbocation in these reactions, and our catalyst is aluminum chloride, just like the halogenation reactions. Okay, so for Friedel-Crafts alkylation, because you have alkyl groups and carbocations involved, you really have 3 different options. So you can have a primary alkyl chloride that cannot have any rearrangement. So that's when the carbon and chlorine bond, after you form that adduct, that bond doesn't break, and you actually keep the chlorine on there, and then the electrons from the ring attack the carbon while it's still connected to the aluminum chloride, if you remember that. If not, I can go through that quickly after I finish explaining this. So you can have that. You can also have rearrangement, just, simple rearrangement, where if you have a primary carbocation about to be formed, but it can't actually be formed, you can rearrange or rearrange. And you can also have a stable carbocation with no rearrangement. Okay, so in this case, this is rearrangement. So our first step is we have our alkyl chloride. These lone pairs of electrons, one of them will attack the aluminum, which will form chlorine aluminum bond. Okay, that forms a negative charge on the aluminum, positive on the chlorine. Okay, so what we want to happen is we want to have a carbocation. So if I break this carbon-chlorine bond, that will put a positive charge on this carbon right here, and that would make a primary carbocation, but we can't actually form that. But we do have a possibility of rearrangement. Okay, so it'll actually rearrange before the carbocation is even formed. So this hydrogen will move to this carbon at the same time as this carbon chlorine bond will break. Okay, so that will form this tertiary carbocation and then that anion. Did we follow that? I can re-explain it if that was confusing. We all good? Okay. So now we have our carbocation. This is our electrophile. So the arrow will go from the double bond to the electrophile, which will add that to one of the previously doubly bonded carbons. Positive charge will form in the other. Again, the carbon-hydrogen bond will break, reform the double bond here. Okay, so just pay attention to rearrangement and pay attention to what can and cannot be formed. Does anyone have any questions there? I know that one's a little bit more confusing, but we good to move on? Okay. I don't remember actually.
What's the question?
Does this require heat?
I
don't think so.
If it does, he normally does. He's not picky about like if you write that it requires heat or not. If on like a test, I actually don't really remember. But like if it does and you didn't put that, he wouldn't take any points off.
Except if it was like elimination or something.
If it was something like really crucial to the mechanism, then yes. I don't think it does, to my knowledge, but you could probably look through the PowerPoint and it'll tell you. Okay. So we can also have Friedel-Crafts acylation, which is putting an acyl group on an aromatic ring. So our electrophile here is an acylium ion, okay, which is this right here. And then our catalyst is again aluminum chloride. So we put an acyl group on a ring by reacting an aromatic ring with an acyl chloride in that aluminum chloride catalyst. Okay, so similar to halogenation and alkylation, you'll form this adduct product here, okay, where the lone pairs of electrons from chlorine will attach to the aluminum. You'll form a chlorine-aluminum bond here, negative charge on aluminum, positive charge on chlorine, and then this carbon-chlorine bond will break, okay, which will give you a positive charge on this carbon. This will be your electrophile, and then you'll form that anion again, okay. So in this case, the primary, secondary, tertiary carbocation doesn't apply because this isn't a true, it's not a normal carbocation because of this carbon-oxygen double bond. So this can actually be formed, and it does. Okay, but this is our electrophile. So again, electrons will come from the double bond and attack that electrophilic carbon, okay, which will add this group to one of the previously double bonded carbons. Positive charge will form in the other. Then again, carbon-hydrogen bond will break. Those bonding electrons will reform the double bond. And the whole point, I guess not the whole point, but an important point of acylation is we can make straight chain alkanes from it. Because in alkylation, if you have any possibility of rearrangement at all, it will happen. Okay, so it's kind of impossible to make a straight chain alkane or a straight chain, what's it called? Straight chain benzene, because of that rearrangement that will occur.
Is this where we shine light?
No.
Straight chain?
No, that's with radical halogenation, which we'll get to that in a minute. But yeah, so if you want to make a straight chain alkylbenzene, okay, so you can react with whatever R group here, okay, and then you end up with this product. And then if you reduce with tin and hydrochloric acid, that'll reduce this carbon, okay, and add 2 hydrogens here, and that will form a straight chain alkylbenzene. Okay, so that's if you want to form like an unrearranged alkylbenzene, which you can't really do with alkylation because of the rearrangement. Okay, so that's the important part.
So acylation is really to form unrearranged straight chain.
So you can form a straight chain alkylbenzene from acylation. Sometimes you do want this product and sometimes you keep this product. But a big important point is that you can make straight chain.
But they're unrearranged. In other words, we don't have rearrangement.
Right, so rearrangement forms like a branched chain alkane. Okay,
Okay,
so
Okay.
yes, straight chain is synonymous to unrearranged.
okay.
I just broke
So
this
how we
pen.
end up with CH2, CH2, CH3 again?
So this CH2, CH3 was already there. This carbon is this carbon, and this is a reducing agent. So reducing means
And
to
the
add hydrogen.
Fragments.
Yeah, add hydrogen or remove oxygen. So we remove this oxygen, add 2 hydrogen. So it's reduced from this to this. Any other questions there? I really just broke this pen, and that's just great because now I can't write on the screen, but that's okay. Okay, so those were just like the general simplest mechanisms there. But when you have side chains or substituents on a group, you can have side reactions with those groups. Okay, so one of them is the one we just talked about. Okay, you have reduction. So if you put an acyl group on a ring, okay, and you don't want this product, you can reduce it to a straight chain alkylbenzene. So that takes off this hydrogen and replaces it with 2 hydrogen here. Okay. And similarly, you can also reduce a nitro group, okay, which is NO2 group. You can reduce it to NH3 ammonia, but this is unstable because of that positive charge. So you can actually wash it in, this is a basic salt, and that will take off one of those hydrogens and give you this, which is stable. This is aniline. Okay, but the big point is that you can reduce the nitro group to aniline. Okay, so opposite of reduction, you can also oxidize. Okay, so if you have alkyl groups, if you oxidize with this potassium permanganate, and these are really the only oxidizing reducing agents he'll give you, is potassium permanganate is an oxidizing agent, and then tin and hydrochloric acid is a reducing agent. But if you have alkyl groups on a ring and oxidize, you'll end up with this benzoic acid group, this carboxylic acid group, okay? And it doesn't matter what this alkyl group is, no matter how many carbons you have on this chain, it will always give you just this. Okay, so this could be a methyl group here, it would still give me this, or a 9 carbon chain, it would still give me this, okay? And if there's 2 alkyl groups on the ring, you can oxidize both of them, okay? And then another side chain reaction I didn't write on here, and now I broke my pen, so now I really can't write it. But I'll try to with the mouse. It's going to be ugly. But so if you have an alkyl group on a ring, and the thing that Carol was talking about, the radical halogenation, so that will put a halogen not on the ring, but on the side group, okay? And that is where you react it with light or heat, okay? And that will replace one of the hydrogens on that methyl group there with a bromine, instead of putting a bromine on the ring. Does that make sense? So it's putting it on the side chain and not connected to the ring. Because if we want to do that, then we do halogenation, where we react with this and aluminum bromide, aluminum chloride. Okay, so that's another side chain.
If you don't use heater like you did in aluminum chloride, it adds to the ring, right?
Yeah, so if you didn't have heat or light and you react with aluminum bromide, then it would put it here, and you would have the bromine group there. Okay. So just keep these in mind. These are going to be important for the synthetic applications part of your test. Okay, so another big thing we went through is substituent effects. So groups that are already on the ring before you have EAS reactions, they have an effect on the rate of the reaction and where the reaction takes place. Okay, so we can either have EDGs, electron donating groups, or EWGs, electron withdrawing groups. Okay, so EDGs will have a lone pair of electrons on the atom that's directly connected to the ring, or it'll just be electronegative in some way. Okay, which can donate electrons to the ring, which the idea is that the more electron density you have in the ring, the faster the reaction will be. So EDGs make the reaction faster than it would be without, with just normal benzene. Just the opposite with EWGs. The atom directly connected to the ring will be partially positively charged, or just have something electronegative connected to it. So that will pull an electron density from the ring, which will slow down the reaction. Okay. So this is just a few of them. This isn't all your examples, but a few examples of EDGs are just alkyl groups, your OH groups, OR groups, NH2. Electron withdrawing group, like a carbonyl group, nitro group, cyanide, halogens. So typically your EDGs are ortho-para-directors, and typically EWGs are meta-directors. The halogens are really the only exception we cover in this course, but EDG or halogens, even though they're EWGs, are ortho-para-directors. So, and I have this illustrated here, but this shows why that happens. So if I have an OH group already on this ring, okay, and this oxygen will have 2 lone pairs of electrons. Pretend that's on the top side of the oxygen, but it has 2 lone pairs of electrons here. So it's an electron donating group. Okay, it can donate electrons to the ring. Okay, so if I have a nitration reaction with this OH group on the ring, okay, if I add it to, and we already know that it's an ortho-para-director, but it's an ortho-para-director because if I add it to the orthocarbon here, if I break this double bond, add it to the orthocarbon here, that will form a positive charge on C1 with the OH group on it. And because this is an electron donating group, it can donate these lone pairs of electrons to the ring, which neutralizes this positive charge. Okay, and the less charge you have localized in one place, the more stable it is. So this benzenium ion is more stable because this EDG and because it's on this C1. Okay, so also if I add it to the paracarbon here, if I break this double bond, add it to the paracarbon here, that'll form a double or a form of positive charge here. And remember, the positive charge can skip every other carbon. So I can, if I move these electrons down, okay, because remember the electrons delocalize in the aromatic ring. So if these electrons move down, this positive charge will move to C1, and I'll have this case again, where the lone pairs of electrons can come down and neutralize that positive charge. Okay, so that's why EDGs, things with lone pairs of electrons, are ortho and para-directors, because I can get that positive charge on C1 and I can neutralize it with that EDG. Okay, so
would it be okay to draw both, or should we just draw like one or the other on these ends?
one second. So I would draw it where, so normally things are ortho and para-directors will be para-directors first because that gives you the most amount of space. So you could just draw this one because it's a given that it's implied that it can spread the positive charge here and then have that stability. So you could just, I don't think you have to draw the several different possible benzenium ions unless he asks for it. Does that make sense?
Yes.
Okay.
So if we do in fact draw the ortho, it wouldn't also be wrong, right?
No, it wouldn't be wrong.
Thank you.
Welcome. Okay.
But we wouldn't necessarily draw the meta unless he asked for it, right?
Yeah, you wouldn't draw it if the reaction wouldn't proceed that way.
Okay.
That makes sense.
I know even in his PowerPoint slides, he shows the meta, but it's not.
Yeah, so he
That's the
shows the meta
1%.
to show you why it's not meta.
Okay.
Okay, so on like the test, you wouldn't draw out an intermediate if the reaction doesn't proceed that way. Okay, but Jemima, NH2 is an EDG because nitrogen has a lone pair of electrons in NH2. Hold on, I'll draw it out. Just kidding, I don't have a pen. I'll do a thing. Okay. So nitrogen has a lone pair of electrons here. Okay, so that's why NH2 is a EDG as well. So typically just things with lone pairs of electrons will be EDGs because they can donate that lone pair. Okay, so this is ortho pair directors, and this is the same for alkyl groups, OR groups, NH2, and there's other examples you can see that I didn't write. So this is a carbonyl group. Okay, this carbon double bonded to oxygen. Okay, and this is an EWG because this oxygen is electronegative. It's pulling electron density towards itself, which forms a partial positive charge on this carbon here. Okay, so that's what makes this an EWG. So that will pull an electron density towards the partial positive charge, okay, which will slow down the reaction. Okay, and this is a meta director because if I add this nitro group to the meta position, I'll form and break this double bond. I'll form a positive charge on this carbon here. Okay, and remember, positive charge skips every other carbon. So I can have the positive charge here, here, or here. Okay. So my goal here, this why it's a meta director, is because I don't want the positive charge here. Okay. Because if I have the positive charge here, if I add this group to an ortho pair carbon, and this positive charge ends up on this carbon, okay, so I would have a full positive charge here and a partial positive charge here, and those will repel each other and form a lot of strain, okay, because they're like charges. Okay, so that will have electrostatic repulsion, which will increase the energy, decrease stability. Okay, so our goal in making these intermediates is just to make the most stable one we can. Okay, and it would be particularly unstable if the positive charge ended up on that C1 carbon with the EWG on it. Okay, following me? Okay, so this won't be a huge part of your test. It'll be mostly EAS reactions, but there's a chance you'll have some nucleophilic aromatic substitution. He'll probably ask you something about it. So everything before what I'm talking about now is electrophilic aromatic substitution, so reacting a benzene ring with an electrophile. Okay, but you can also react an aromatic ring with a nucleophile. Okay, and that will also give you a substitution reaction. So the general equation, you'll have a halobenzene react with a nucleophile. Okay, so you can have OH, NH2, cyanide. These are pretty much the only ones he went over, the only ones he'll give you. And you'll end up substituting that halogen with your nucleophile. Okay, so the mechanism here, you have your base. Okay, these lone pairs of electrons will take this hydrogen. Okay, this CH bond will break, and these CH bonding electrons will form a triple bond here. Okay, this is called a benzyne intermediate. Okay, and when you form this triple bond, that'll push off this chlorine, so that bond will break. Okay, so we lose water and we lose chlorine. Okay, so here's our benzyne intermediate. So now we have another molecule of our OH. Okay, that will attack one of the triply bonded carbons. Okay, and this is a symmetrical benzyne, so it has equal chance of attacking both triply bonded carbons. It'll attack both 50-50, and you'll see that's the same case even if there's another group here. So there's no substituent effects here. No matter what's on the ring, this will have equal chance of attacking whichever triply bonded carbon. Okay, so if I do that, I'll attack this carbon, which will break this triple bond, and these bonding electrons will stay on that other previously triply bonded carbon. Okay, so I added the OH group here. Okay, and then this actually forms a negative charge on that other carbon because these electrons just stayed here. So this is more electrons, so it's negatively charged. Okay, this is unstable. I want to get rid of that negative charge. So this carbon will attack this hydrogen, which will break this oxygen-hydrogen bond. Okay, and then I'll form, that'll add this hydrogen here, which will get rid of that negative charge, and it'll form the product. Okay, so like I said, that won't be a big, huge thing on your test, but you'll still need to know the basic mechanism for that. And you can also do this with other nucleophiles and unsymmetrical rings too.
When it attacks, the negative charge attacks the HOH, the OH leaves and the hydrogen goes where?
So the hydrogen gets added to this. Yeah, right. Because we took a hydrogen here, okay, formed a triple bond, so we just put that hydrogen back. Okay, and that gives all of these one hydrogen, except for this one with the OH group.
Plus we have the hydroxide anion.
Mm-hmm. Okay, any other questions there? Okay, so I have a few examples of something you might see on the test. So he might give you something like this and ask you how to make it. So you'll have to think about all the nitration, blah, blah, whatever reactions, and then your side chain reaction substitution effects. So you'll have to apply pretty much everything in the section. So what should I do first here, my friends?
You could add the nitrile group and then to benzene. Start out with benzene and do a nitration.
Okay. Is a nitro group, what kind of director is a nitro group?
Oh, it's an electron withdrawing group.
Which is what director?
A meta director.
And these groups are para to each other. Okay.
Right.
So if I put this nitro group on first and then try to put this here, then it would end up on a metacarbon. These are para to each other.
Okay, so we do the oxidation first.
Oxidation of what? Okay.
So we start out with toluene and we oxidize it, right?
Okay. So hold on. Okay. So if I put an acyl group on there, that gives me a carbonyl group. What director is a carbonyl group?
It's an electron withdrawing group.
Yeah, so it's still meta. So if I put that group on first and then do nitration, then I'll still have meta, but I want these para to each other. Okay. So I know I have to start with benzene anyway. Right. Okay, so if we start with benzene ring, okay.
Do we have to start with benzene or can we start with toluene? Like, a methyl group on it.
I think he'll probably ask you how to make it from benzene and then whatever other
Okay.
reagents. Okay, because you make toluene by doing this with benzene.
Okay.
Okay. So I know I can oxidize whatever alkyl group to that benzoic acid group, right? So typically you would just pick
Use
whichever
methyl
smallest
chloride.
one. Yeah.
Methyl chloride
So could react with
in
methyl chloride.
Friedel-Crafts reaction, AlCl3.
hmm Okay, so this will give me Friedel-Crafts alkylation, okay, which will just add that methyl group to the ring, okay? And an alkyl group is an ortho-para director, okay? So I want these two groups paired to each other. So now that I have a para director,
Now do nitration.
now you can do nitration.
Plus HNO2 or 3. HNO2.
It's 3. Okay, do that in sulfuric acid. Okay. That will give me nitro group para to a methyl group. Okay. But that's not the product I want. Okay, so I want a carboxylic acid group here. Okay, so how do I do that?
Now you do oxidation with potassium manganate.
Mm-hmm. Yeah. So now that these groups are paired to each other, now I can oxidize with potassium permanganate. Okay, which will give me that. Okay. Everybody follow that? That's very similar to something he would ask you, is he would just give you something with multiple substituents and ask you how to make it from benzene.
And so we would call that nitrile benzoxide.
So this, I believe, would be called p-nitrobenzoic acid. Okay, because this here is just benzoic acid, and then we have a nitro group para. So you would call that p-nitrobenzoic acid, I think. Okay. So another thing that he might ask you to do is to give you a benzene and then a few consecutive steps and ask you what that would form. Okay. So if I have benzene and I react that with chlorine and aluminum chloride, okay, that will just put a chloro group on the ring, right?
Right, and also you gave Cl.
Right. So I didn't write out any of the byproducts really.
Okay.
Sometimes he writes them, sometimes he doesn't. I would on the test just to be sure. But because they're byproducts, because they're not organic, we don't necessarily really care about them. So you can write them if you want. I probably would just to be safe, but I don't. He wouldn't count it wrong if you didn't write out the byproducts, okay? Because this is a product we really care about anyway. So that would give me the first step. Okay. So then if I react this with, what did I even write there? Because I can't see it. This methyl chloride. Okay. What director is a chloro group?
It's a electron withdrawing group. So it would direct on the meta.
That's the exception though, isn't it? That's not what I wrote.
Well,
So it's an electron withdrawing group, but it's an ortho pair director.
Okay,
Remember that?
okay,
Because that's the exception. Okay, because most EDGs are ortho pair directors, most EWGs are meta directors. Halogens are the exception. Okay, and that's because of the electronegativity. Because even though they have lone pairs of electrons, you think they would be EDGs, but they're electronegative, okay, which makes them EWGs. Okay, but the whole positive charge thing still applies to halogens, so they're ortho pair directors. Because if I put positive charge on C1 with that chloro group, the lone pairs can neutralize it, okay? But because it's electronegative, it's a weakly deactivating group, a weak electron withdrawing group. Follow me?
so it only directs to the pair on carbon because the positive charge would go on the metacarbon and it skips every other carbon, so the positive charge would help stabilize it because it would go on C1.
Mm-hmm.
Yeah.
Okay, so this is an ortho pair director, okay?
Yes.
So I can have here at ortho or at para. Okay, so those are my products for that step. And then if I oxidize that in potassium permanganate, my oxidizing agent, okay, that will just turn these methyl groups into carboxylic acid groups.
Well, he wanted us to list both groups in that one, like pair director and ortho.
So typically, ortho pair directors will first direct to the pair carbon to again get the most amount of space. I just wrote that because it's an ortho and pair director, but I think you should be fine if you just put the pair one, because
Okay.
I'm pretty sure that.
Can we make sure he won't take points off? Can we ask him?
Sure.
So we don't have to write the mechanisms on this, right?
If he asks for it, yes. But if he just asks what's the product of these consecutive reactions, blah blah, then he wouldn't need to put the mechanism. If he wants the mechanism, he'll ask specifically for the mechanism. Okay, and then he'll also ask you for the basic nitration, blah blah, all those reaction mechanisms.
Okay. But he won't ask for the mechanism for the potassium oxidation.
No, he won't ask that. Okay, one last thing I wanted to show you. I don't think it'll let me. Well, let me click on that link. It might.
So my question to you, my dear,
Mhm.
he said that this test is generally easier for students. Do you think so as well, or?
To be honest, I don't really remember it. I don't. It's equally long, I would say. I think the tests from this semester are generally longer than the ones. There's more questions than from last semester. I don't remember it being harder for sure. I wouldn't say I remember it being easier, but I mean, he would know, he grades them, so. I guess.
Generally, I'm finding it much easier than the last time.
Yeah. It's been a long time, so I don't remember how I did. I did fine on both of them, but I surely don't remember it being harder, if that is any solace to you. Okay, let me share my screen so I can show you something. Okay. Hopefully you can see this, but I found this website in my inorganic class because I used it for that. But I just wanted to show you guys this in case you're more visual learners and you would benefit from some more visuals. So this website is called ChemTube 3D. It has just like interactive chemistry things across like organic, inorganic, even like, stuff from Chem 1 all the way up to stuff I'm doing now in like 400 level classes. So it's pretty helpful. It has a tab under organic, has a tab for electrophilic aromatic substitution. So you can click on whichever one, and I'll kind of show you. So it'll just show you like the molecules and what's happening within the mechanism. So you can click on it. This is nitric acid, this is sulfuric acid. So what's happening is the electrons go from the OH on the nitric acid to take a hydrogen off of sulfuric acid, blah, blah. But if you click the arrow, it'll actually show you the orientation of the molecules and how that happens. Okay, and then you end up with, this is your OH2 on your nitric acid. Okay, and it'll show you that bond breaks off. Okay, and then you end up with the nitronium. Okay, and water.
Nitronium is 180 degrees. Will he ask us about 180 degrees, 120 degrees, and
No.
none of that? Yeah.
No.
It's less than 100.
Yeah, no, he won't ask you about shapes of molecules or anything. Yeah, he wouldn't ask you about that.
And you mean to tell me Dr. Taylor showed you this?
No. No, I found it. Yeah, I found it because we were working on like symmetry, which is highly confusing and inorganic. But so yeah, it'll just go through the mechanism and show you all the steps, like with just interactive little like videos. So just, you may or may not benefit from that. It's worth checking out though, and there's a few different tabs. There's stereochemistry, if you want to revisit that, like SN1, SN2, elimination reactions. Okay, and it goes all the way up to advanced organic stuff. So just keep that in mind if that would be helpful to you. But that is all I have. Unless you guys have any questions, feel free to put them in the chat or unmute. But if not, you're free to go, my friends. You're very welcome.
Got the actual